Hi guys, Dr. Kruse here, Elementary Statistics. We're still doing hypothesis testing. This is another hypothesis testing video using the traditional method where we see if our challenge lands in the critical region. And we're going to deal with proportions on this video. Now I'm going to be using a 5-step process, and I explain it in more depth. Whoops, that's not the right one. I explain it in more depth on this video here. So if you haven't watched this video, go back and watch it if you don't understand the 5-step method. All right, now recall what we're going to do here. We are basically going to set up a normal distribution curve, and we're going to have rejection regions shaded. I might have the left tail shaded, I might have the right tail shaded, or I might have both of them shaded. That's our 3 tests. If we challenge that, that the proportion is less than, we're going to shade the left tail. If we challenge that the proportion is greater than, we're going to shade the right tail. And if I just challenge that the proportion is different from what is claimed, well, then I'm going to shade both tails. And we're going to have to look up the proper z numbers so that we draw the line in the correct place. It might be over here, here, here. We got to figure out where to draw the line for our particular challenge. All right, so I'm only going to show you like 3 problems on this because there's been 2 previous lessons to this, and they all use the same 5-step process. USA Today reported that about 47% of the general consumer population of the United States is loyal to the automobile manufacturer of their choice. Suppose Chevy did a study of a random sample of 1,005 Chevy owners and found that 481 of them said they would buy another Chevy. Does this indicate that the population proportion of consumers loyal to Chevy is more than 47%, and use alpha equals 0.01? Excuse me. Okay, let's break that down. So the claim is, all right, the claim is, that's how we're going to state our challenge. We got to first we got to figure out what they're claiming, what the accepted belief is, what the accepted average is. So the USA Today reported that it is believed that 47% of people stick with, their favorite brand of car. So that's going to be our null hypothesis here in a minute. We're just going to say that the population proportion is 47%. All right. What else do we have here? This is going to be N. How many people did you sample? How many people did you survey? That's going to be N. And then out of that, this is the hint that you're going to be dealing with the proportion. When they say out of 1,005, 481 did this thing, well, that's a fraction. And that fraction is what we're going to turn into our sample proportion. We're going to call it P hat. We put a little hat over the P. The proportion is how many did the thing that you want out of how many people you sampled. So 481 said they would buy another Chevy out of 1,005 people that we interviewed. All right. Now, this fraction here, this proportion, this is the exact proportion, all right? If you change it to a decimal, that's fine, but know that most of the time these fractions are going to turn into messy decimals that go on forever, and you're going to have to round that thing. And if you do your calculations with a rounded number, lots of times your answer will be off a little bit. Now, if you must, if your teacher tells you you must use a decimal, then my advice is go at least 4 decimal places. So if I was going to use this decimal, I would use 0.4786. I would use at least 4 places after the decimal, and most of the time that'll get you the right answer. But if you want the absolutely right answer, use the exact fraction in your calculations. All right, let's talk about P and Q. Now, P is the accepted belief. All right, the accepted belief is that 47% would buy another Chevy. Q is kind of the rest of the 100%. Like if I told you there was a 47% chance it's going to rain today, well, that means there's a 53% chance that it will not rain. So this is called probability of success, the thing that we're measuring, and this is probability of failure. Easy way to find it, easy way to find 53% is just take 100% minus 47%, which is what we did here, only we're speaking decimal. 1 minus 0.47 is 0.53. So there's a 47% chance of success. There's a 53% chance of failure. This is our sample. All right, we sampled 1,005 people, and we came up with our own proportion. A proportion is just a fraction. We came up with our own proportion. All right, and we're going to run a test. Now look at ours. Ours says 0.4786. That's a little higher than 0.47. See this here? That's a little higher than 47%. So the accepted belief is that 47% will buy the same car again. Our test, our sample of 1,005 people, looks like it's a little bit higher. All right, so that's probably going to be our challenge. Our challenge is going to be, no, 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 this isn't right. I believe it's a little higher based on my sample. And we're going to run that test and see if my numbers are high enough to matter, to see if they're significant. The level of significance, A, alpha, that we're going to use is 1%. And then this final thing over here on the right is we just got to kind of test our numbers and make sure that we have enough samples, enough people in our sample that the conditions will be met, and we can assume that the curve will be approximately normal. If it is, we get to use a z-score. If it isn't, we use a t-value. But today we're just going to use a z-score. So let's just double check. The number of people times the probability of success, the proportion of success, is 1,005 times 0.47. That's 472.35. I just got to make sure that's bigger than 5. Of course it is, so that one checks out. But the other one has to check out as well. The number of people times the proportion of failure. So 1,005 times my proportion of failure, 0.53. That's 532.65. That's bigger than 5 also. As long as both of them are bigger than 5, the conditions for a normal distribution are met. And if it's a normal distribution, we can use a z-score. All right, first step in the 5 steps that I use is state your null hypothesis. That's H sub 0. 0 means null, all right? This is the accepted belief, the advertised claim. They are advertising, USA Today is advertising that 47% buy the same car again. So the advertised proportion, think of this as a fraction, 47 out of 100. The advertised fraction or the advertised proportion is 47 out of 100, or 47%, or 0.47. We'd rather use the decimal here. My challenge is, I said, hey, I did my own test here, and I had 481 out of 1,005, which is a little bit higher than 47%. I'm going to challenge the accepted belief. I'm going to challenge your advertised claim. I'm going to say, no, 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 you're wrong. I'm going to say it's actually much higher than 47%. And we're going to have to run a test and see if it is much higher. It looks like it's a little bit higher, but the question is it significantly higher? Is it high enough that people care? If it's just a little bit higher, nobody's really going to care. So we got to figure that out, whether it's significantly higher, whether it makes a difference, whether anybody cares about it. All right, next step is draw your curve. All right, I like to plot the curve and color in my rejection region over here. Now it's a right-tailed curve because we're doing the greater than. All right, we're choosing to challenge that. No, it's not this, it's more than that. It's greater than, it's over here on the right. So my rejection region, how big it is, depends on your level of significance, your alpha. And our alpha is only 1%. That's a pretty small rejection region. This is called a critical region, also called a rejection region. The point is, if my test statistic lands in here, I get to reject what they said. All right? They say the proportion is 47%. If I run my own test and my dot lands over here, I get to say, no, it's not. I said, what you said is not right. So I get to reject the advertised claim, or I get to reject the accepted belief if my dot lands in here. Now, before we figure out where the dot lands, just pretend you don't see the dot over there. Before I see where the dot lands, I have to figure out where to draw the line for the 1%. So there's several ways of doing this. Remember, we're using the z-table. What I need is 1% shaded, which means 99% over here in the white. So 99% here, 1% there. That's what my alpha is telling me. What I need is the z number that has 99% of the area of the curve to the left. And there's several ways of looking that up. All right, we can look it up the long way here. So I'm looking for an area of 99%. And I look in here And there's 99% and a little extra, 99% and a little extra, 99% and a little extra. There's 99% and just a tiny bit extra. That's about as close as I'm going to get. So there's my 99% to the left. Now, what Z number was it that created that? That's 2.3, and then we go to the top of the column, 3, 2.33. So that's kind of the long way of finding it. Find 99% in your table, and then figure out what Z number produced that. There's a quicker way. If you have this little cheat sheet down here, we're doing a 1% level of significance, and we're doing a right-tailed test. And it's going to tell us if you're doing 1% and a right-tailed test, you need to start shading at 2.33. This is where we're going to draw the line. All right, so we're going to draw the line right here about 2 1/3 steps to the right. Here's 0, 1, 2, and that's about 1/3 of another step. So about 2 1/3 steps to the right, that's where I draw the line, that's where I shade, and that gives me 1% here and 99% over here. Now, you guys that like to play on your calculator, it's pretty easy to find this on your calculator. Let me clear that. You just go to distribution here. So second function, distribution, and I want inverse normal. What that means, inverse means backwards. All right, I'm going to give it the area, and it's going to work backwards and tell me what the t value is. So I have a normal distribution. I'm going to give them the area. They're going to look around and figure out what Z number I need. All right, so I need to put in the area. The area to the left of this is 99%. Let me clear that and put 99% in. It says, what's your average? Well, it's always 0 in the middle, and we go by ones when you're doing a normal distribution curve. I paste that into my window, hit enter one more time, and there's your 2.33 right there. On the 84, it's super, super easy. But the 83 does it too. I mean, if you like to play on your calculator, same thing, go to distribution. So second distribution, and you want inverse normal, which is the third option. Now the 83 is just tougher because it makes you enter the numbers. So you want 99% of the curve to the left, and then you need a comma. Your comma is right here, comma. And then you got to tell it what's the average. Well, the average on a normal curve is 0 in the middle. And then comma, and then they ask you, okay, how big are your steps? How big are your standard deviations? We're going one step at a time. Close your parentheses, and you wind up at the same place, if you like to look those up on the calculator. But it's pretty quick to do on the table. If you have the table handy, just grab the table. All right, step 3 is calculate my test statistic. So it's called a test statistic. We usually label it as Z star. All right, this is based on my data. So my data is P hat. That's the owners that I surveyed, all right? And I got this proportion right here, all right? If you use the decimal and it's messy, make sure you go at least 4 decimal places and you'll usually wind up at the right answer. If for some reason it's not accepting your answer, don't use this and use the fraction in your calculations instead. But most of the time, all right, if you go 4 places past the decimal, you'll be okay. So on my data, I say it's a little higher than 47% minus the advertised claim, all right, the accepted value, the accepted average, minus the accepted value of 47% over, and now this is basically a standard deviation calculation. I need P, that was 47%. Go back to your data and look. Q, that's the proportion of failure, 53%. Divided by how many? 1,005. And we get a test data value, a test statistic of 0.55. So that tells me to place a dot about half a step, 0.5 is a half, about half a step to the right. Here's 0, that's about half a step to the right. That's where my test landed, all right? So now I got to make a decision. I wanted it to land over here because I'm challenging the advertised claim. I'm challenging the accepted average. I wanted to say, no, that accepted average is wrong, all right? But I ran my test. It landed over here in the accept the null hypothesis area. So basically what I have to do is I have to accept what they say. They said the proportion was 47%. I was arguing that it was not. I was arguing that it was greater. That's my challenge. My challenge failed, all right? I landed in the area where I have to accept what they say, okay? Now, of course, we can't say it the easy way. The easy way is to accept what they said. We have to say it the hard way. We have to say fail to reject the null hypothesis. I was trying to reject it. Remember, we were arguing with what they said? I was trying to reject it, and I failed. So then number 5 is just basically kind of explain it to Grandma. All right, Grandma doesn't know what all this stuff means. And you're just going to tell Grandma in English, there is not enough evidence. All right, we failed. We didn't gather enough evidence at the 1% level of significance to conclude that. And then after the word that, you just basically restate your challenge. So I'm basically saying I did not have enough evidence to back up my challenge. And my challenge was the population proportion, sometimes called the true proportion, of consumers loyal to Chevy is significantly more than 47%. That's what I was trying to prove. I was trying to say, no, it's more than 47%, but my test failed. So I have to say that. I failed to prove you wrong. I did not have enough evidence to prove you wrong. All right, let's do a couple more here. The U.S. Department of Transportation, National Highway Traffic Safety Administration reported that. This is the advertised claim. This is the accepted average, the accepted mean, the population proportion. So they're reporting that 77 out of 100, because these are proportion problems, so think of it as a fraction. They reported that 77 out of 100 of all fatally injured automobile drivers were drunk, intoxicated. A random sample of 50, there's our N, a random sample of 50 records of automobile driver fatalities in a certain county, they didn't name the county, showed that 33 involved an intoxicated driver. So out of 50, 33 were. All right, we're going to call this success, even though this is kind of a morbid problem. We're going to say 33 out of 50. That's going to be our proportion of drivers that were intoxicated. We're going to say 33 out of 50 is success. That's going to be our P. P hat, excuse me, because this is our sample. P is 77%. Nationally, the nationally accepted average is that 77 out of 100 are intoxicated. We did our own test of 50 and found that 33 out of 50 were intoxicated. We're going to compare my data with the accepted average, and we'll come up with a challenge here in a second. Do these data indicate that the population proportion, or the true proportion, of driver fatalities related to alcohol is less than 77%? So there's our challenge right there. Based on my test, 33 out of 50, I'm going to challenge that this is no longer true. This is no longer the true average. I'm going to say the true average is actually less than that. Use an alpha level of 5%, so level of significance 5%. This is less than, that means we're going to color to the left. This is going to be a left-tailed test, less than, to the left. So I'm going to have to shade 5% of the curve to the left. All right, organize your data. We did 50 samples. We sampled 50 records. The accepted belief is that 77 out of 100 involve an intoxicated driver. The proportion of failure would be the rest of that 100. If 77 out of 100 are intoxicated, that means 23 out of 100 are not. You can just do 1 minus 0.77 to find Q. So proportion of success, 77 out of 100. Proportion of failure, 23 out of 100. This is the accepted belief. I did my own sample of 50 drivers and found that 33 out of 50 were intoxicated. All right, if you change that to a decimal, it's actually a really nice decimal, 0.66. It stops right there. That's called a terminating decimal. It doesn't go on forever. So using 0.66 in your calculations is just fine. That's exact. It's just as exact as this fraction. All right, so look at what they claim and look at what we came up with. They claim 77% are intoxicated. We did our own little survey and we said, nuh-uh, only 66% are intoxicated. All right, so it obviously looks like our sample is lower than what is believed to be true. We have to go ahead and run a test and see if it's so much lower that it's significant. We got to make sure it's low enough that people care. Alpha level of significance is 5%. And then we just run our test over here real quick to make sure that my data is going to, be approximately normal. N times P, 50 times 77%. That's 38.5, which is greater than 5. Check. N times proportion of failure, 50 times 23%, that's 11.5. That's greater than 5, check. So we can assume that our test and our curve is going to look approximately normal. All right, set up your hypothesis. So H sub 0, this is the null hypothesis. Null means 0. The null hypothesis is what is believed to be true. That's always going to be in equals. Lots of people get confused about that. Basically, it's up here in your data. This is going to be your null hypothesis with the equal sign. So it's believed that 77% are intoxicated. My challenge, alternate hypothesis, H sub 1, my challenge is no, the true proportion of people that are intoxicated is less than that. Now we got to run our test and see how it works out. All right, so draw your curve. Step number 2, I always draw the curve. I need 5% shaded to the left. Less than is a left-tailed test. So you're definitely going to shade, and you want 5% here and 95% on the white area. And you got to figure out where to draw the line. So we need to look up a z number that has 5% of the curve to the left. And like I said, there's several ways of doing it, but the easiest way is to cheat. Go down to your cheat sheet here. If I want 5% and a left-tailed test, I need to draw the line at negative 1.645. All right. You can do it on your calculator, or you can do it the hard way, whatever floats your boat there. So I'm going to draw the line a little more than 1.5 steps to the negative, to the left. Here's 0, there's 1, there's 1.5, and then 1.6 would be a little bit further to the negative. Draw your line, shade it. Now we've shaded 5% of the curve to the left. That means 95% of the curve is here on the white. Let's run a test and see where our dot lands. Pretend you don't see that dot because you haven't run the test yet. So we run the test and pop the numbers into the formula. Z star, our test statistic, is my data minus the accepted belief. My data is 66%. The accepted belief is 77%. We're seeing the difference. I need to see if that difference means minus, I need to see if that difference between the two is significant. And then divided by, this is basically a standard deviation calculation, which tells us how many steps to the right or left of 0 we're going to go. Divided by P, so the accepted proportion of success is 77%, times the accepted proportion of failure, 23%, divided by how many in my sample, 50, comes up to negative 1.85. That's going to be my dot. All right, I'm going to place it 1 and 85 hundredths of a step to the left. So that's almost 2 steps to the left. Here's 0. Here's 1 step to the left. There's 2 steps to the left. It's going to be a little bit short. You just got to kind of think of where it is in relation to your z number. My z number is 1.6 steps to the left. My test data is 1.8 steps to the left. So this is further to the left. 1.6 steps to the left, a little bit further would be 1.8 steps to the left. So I am just barely in the rejection region, this critical region. All right. I mean, that's good news if you like to win, because we challenged, we said, I took a sample and I believe that the true proportion is actually less than 77%. If I run my test and my dot lands here in the rejection region, I get to say, hey, I win. What you believe to be true is wrong. The null hypothesis is wrong. All right, so therefore I reject what you said to be true, what you accepted to be true. I reject what you said. And then basically the same wording here. You'll notice that really the only thing I change is not to is. So since I won, I'm going to say, hey, I had enough evidence. There is enough evidence at the 5% level of significance to conclude that. And then after the word that, just kind of restate what your challenge was. My challenge was the true proportion, or the population proportion, of driver fatalities related to alcohol is less than 77%. That was my challenge. And I had enough evidence to reject what you said. All right, last one here. And if you got the hang of it, just pause the video and see if you can work it out on your own. See if you can get your data to match my data. In a fishing lodge brochure, the lodge advertises, this is the advertised claim, the accepted average, the population mean. All right, what is believed to be true? So the advertised claim is that 75% of its guests catch a northern pike that's over 20 pounds, so like a big fish. So the lodge is advertising that 75% catch big fish. Suppose that last summer, 56 out of a random sample of 83 guests did, in fact, catch a big fish. All right, so we did our own sample. We're testing that sign out in front of the lodge. You know, there's a big sign that says, hey, 75% of our guests catch a huge fish. We're going to challenge that. So we did our own sample. We sampled 83 guests, and 56 of them said, yeah, I did catch a big fish. So this is the advertised claim, 75 out of 100. Our sample is 56 out of 83. And we're going to compare the two and see if the difference is big enough to matter. Does this indicate that the population proportion, sometimes called the true proportion, of guests who catch pike over 20 pounds is different from 75%? Different from is going to be a two-tailed test. We're not claiming that it's less than. We're not claiming that it's more than. We're just saying it's not 75%. We're saying it's actually a lot different from 75%. It's got to be significantly different from 75%. If it's 74.9%, you know, just a tad bit under, nobody's really going to care. If it's 75.1%, nobody's probably going to care. So it's got to be a big difference. It's got to be a lot lower or a lot higher. Use an alpha level of 5%. All right, organize your data. We sampled 83 fishermen. All right, the accepted proportion, the accepted belief is that 75% catch big fish, which means that 25% don't. Proportion of success, proportion of failure. P hat is my data, and I said out of 83, 56 caught a big fish. Now this is this nasty decimal here that goes on forever. Again, my recommendation is don't use a rounded decimal. Go back and use the actual fraction in your calculations. But if you're told to, you know, round this or whatever and use this in your calculations, my advice is use at least 4 decimal places. So if I was going to use this decimal, I would use 0.674, and that 9 is going to round that up to 7. So I would use 0.6747. Use at least 4 decimal places if you're going to use the decimal. But if you want a more precise answer, use the fraction. Alpha level 5%. Now, we're going to do a two-tailed test here, so I'm going to have to split that 5% into 2 parts. We'll do that in a second. Check your conditions, because you want to know if your distribution is going to be like a normal distribution curve. N times P, 83 times 75%, gives us 6225. That's bigger than 5. Check. N times proportion of failure, that's 83 times 25. That's 20.75. That's bigger than 5. As long as both of them are, you can continue, and you can assume that your distribution is approximately normal, and you can use the Z table. You can get a Z score. All right, state your hypothesis. The sign outside the lodge says that 75% catch a big fish. My challenge is, no, they don't. All right? I'm not saying they catch less. I'm not saying they catch more. I'm just saying they don't catch 75%. Draw your picture. Okay, here's where we got to talk about alpha. Now, I need 5% of the curve to be shaded. Now, in the previous examples, we shaded 5% to the right, or we shaded 5% to the left, but I need the total shaded area to be 5%. When you do a two-tailed test, you need to split that into 2 equal parts. So I need to divide this by 2. 5% divided by 2, you can do it on your calculator, is 2.5%. 2.5%. I probably should have written that here. That's point, I'm trying to write kind of sideways. Oh, this is horrible. 0.0250. Yeah, that's terrible handwriting. But 0.05 divided by 2 is 2.5%, 0.025. And then I just put a 0 on there because it's easier to find in the table. So what I'm looking for is I'm looking for a Z number here and a Z number here that'll give me 2.5% on the left and 2.5% on the right. Now this one's kind of hard to find, so I'm going to go find this one, all right? Because over here, all I have to do is find an area of 2.5% and find the Z number that produced that area of 2.5%. Okay. I'll do it the long way just for grins. All right, let's find 2.5% the long way. So I'm looking for 0.0250. And there it is right there, 0.0250. That's 2.5%. Now what z produced that? Negative 1.9. And let's follow it up to 6. So negative 1.96. And then of course there's a quicker way if you use your cheat sheet. All right, we want a 5% level of significance. That means we want 5% of the curve shaded, and I want it to be a two-tailed test, so I need that 5% split, 2.5 on the left and 2.5 on the right. They're telling us you need to start shading or draw the line at both of the 1.96s, both the positive and the negative 1.96. All right, so draw the line. Ask yourself, where do I draw the line? Draw the line at negative 1.96. That's almost 2 steps to the left. Here's 0, 1 step to the left. There's 2 steps to the left, so just a little bit short of 2 steps to the left. Shade, that's 2.5%. And then almost 2 steps to the right. So there's 1 step to the right, there's 2 steps to the right, a little bit short of 2 steps to the right. That gives you half of alpha. That gives you 2.5% on the right. So 2.5%, 2.5% for a total of 5% shaded. Alpha tells you how much to shade total. Run your test. All right, here's my data. I went ahead and used the decimal, and I went 4 decimal places. So my data, my proportion says that 67% caught a big fish. Mine is what they claim on the board out in front of the lodge. They claim 75%. So it looks, from my data, it looks like people actually catch less than that. But that wasn't my challenge. My challenge was just different from, could be less, could be greater. All right. My challenge was not less than, but that's what the data looks like. It looks like my data is significantly less than this, but let's see where it lands. All right, adjusted standard deviation down here, 75% proportion of success, 25% proportion of failure. 83 people were sampled, and it comes up to a z number of negative 1.58. So my test statistic is going to be about 1.5 steps to the left. So here's 0, here's 1 step to the left, there's 1.5 steps to the left. All right, this is clearly in the white area. This is where I lose. All right, if it lands here, I get to reject what they said. If it lands here, I get to reject what they said, but it didn't. All right, it landed right here. So I have to say, okay, you were right. I was going to say, even though my data looks like it's smaller than what you claim, it's not small enough to matter. All right, I have to accept that the true proportion is 75%. Even though my data argues that, it just wasn't off enough to matter. So I failed to reject. I have to accept what they said. I tried to reject what they said, and I failed. All right, so there's not enough evidence. I did not have enough evidence at the 5% level of significance to conclude that, and then restate your challenge. You can say the true proportion or the population proportion or the advertised claim. You can say anything you want there. Of guests who catch pike over 20 pounds is, I like to add significantly, except I spelled it wrong. There's a C in there that's missing. Significantly different from 75%. You're basically just admitting failure here. I tried to prove their claim wrong, and I failed. I did not have enough evidence to conclude that, my challenge different from 75%. All right, guys, that's it.